In this lesson, we're going to use something called matrices to make this whole solving a 3x3 triangular form process a little more efficient. So when we solve several equations, we want to use a matrix to forget about the variables and deal only with the coefficients. So we're going to create something called an augmented matrix. And then I will define exactly what a matrix is down here. But let me give you an example first to show you. If I have this system here, it's a 3x3, 3 equations and 3 variables. Basically, what its equivalent augmented matrix looks like is this. I have square brackets, and all I'm going to do is take each coefficient and the answer and just put them in this set of brackets. No equal sign, no nothing. So my first row is 3, -2, 1, and 5. You put them in just like that. You're lifting them up and just putting them over in this bracket. My second row is going to be 1, 3, -1, 0, and the third row is -1. Now, since I don't have a y value here, I'm going to put a 0 in because that's essentially the coefficient when the variable isn't there. 4 and 11. This is what we call an augmented matrix, and we need to understand that term because that's an operation in our graphing calculators, and you will look for it. When I say solve using an augmented matrix, this is the type of matrix I mean. It has 3 rows and 4 columns to it when I'm solving a 3x3. So let's define what a matrix is. You guys have probably all heard of the movie The Matrix. And whenever in that movie they show the computer system and they show a whole bunch of numbers on the screen. Well, the whole bunch of numbers make up the matrix because it's defined as this. It's an m by n matrix. That's kind of the size of it. That's a rectangular array of numbers. So I have rows and columns, and this means I have m rows and n columns. So that's important. The order of these letters. If I'm going to tell you how big this matrix is, I always tell you the number of rows and then the number of columns. So that's how it's defined. And it's basically a big rectangle with a couple brackets that has a whole bunch of numbers in it. So if I look at this, I have a whole bunch of generic numbers here. And here it says Aij. We call that an entry. And if I were to specify this entry, that means I'm in row I and column J. So I don't want to say this. I want to say in row I and column J. So the row always comes first. Okay, row I, column J. So I'm going to show you again, if I give you this system of equations and I want to find the augmented matrix, all we do is get our big brackets, we lift every coefficient, and answer and just put it in the brackets over here. So let me fix that. Alright, so if I look at this, my first row is 2, 5, -3, and 1. And that's what goes in there, 2, 5, -3, and 1. Second row is going to be a 0 for the x, a 1 for the y, -2, and -7. 0, 1, -2, -7. Finally, the third row is going to be 3, 4, 0, and 10. So that's what that looks like. So now we're going to do the same thing that we did yesterday, but we're going to deal with the augmented matrix instead of all the equations. It's just a little more efficient because really when you look at it, all we are really manipulating are the coefficients and the answers. We're not doing anything with the variables, so why write them all the time? I'm going to quickly review the steps for Gaussian elimination, and those steps, there's 3 of them. The first one was to eliminate the first entry in the second row. So now I'm going to use that term, the entry, instead of the term, the variable. So the first entry in the second row. So if I were to name that term, that would be A second row, first column. I'm going to eliminate A21. If I'm looking at this example up here, that would be this guy right here. Second row, first column. Next, I'm going to eliminate the first entry in the third row. So that's going to be A31. Finally, I'm going to get rid of the second entry in the third row. That's this guy here. And that's A32. So that's the same process we did yesterday. The next thing I want to show you is a little bit of notation. Some kids like this, some kids don't. It's helpful for me when you do these problems. It tells me kind of what your process is. So I'm going to try to explain that to you. All right, so the notation I'm going to show you is it's used to kind of tell me what you're doing in each step, so you can keep track of what you intend to do. And we use capital R to represent the rows. So if I say R sub 1, that's going to stand for row 1. R sub 2 would stand for row 2. R sub 3 would stand for row 3. So that's just an identifier. Then if I did something like this, 2R1 plus R2. What that tells you is that I'm going to take row 1, and I'm going to multiply every term by 2, and I'm going to add that value to R2. So here this all is in words. I'm going to multiply row 1 by 2 and then add it to row 2. The single arrow represents I'm going to add row 1 to row 3, and then I'm going to place the answer back in row 3. So here's that written out. I'm going to add rows 1 and 3 and place the answer back in row 3. Finally, when I have the double arrow, that just means I'm switching the rows. I'm going to switch row 1 and row 2. Switch row 1 and row 2. So I'm going to demonstrate this with the final example again, and then we'll practice this more in class. Alright, I'm going to demonstrate using that notation and using augmented matrix to solve a system of 3 by 3. So here we have our 3 equations and our 3 variables. I'm going to create the augmented matrix by just lifting all the coefficients and the answers and putting them in the bracket. So we have 1, -1, 3, 4, 1, 2, -2, 10, and 3, -1, 5, and 14. There's my augmented matrix. So to solve this, the first thing I need to get rid of is the 1 in the second row. First column, second row. To do that, I'm going to multiply the first row by -1, add them together, and then put my answer back in row 2. So here's what these symbols are all about. Here's this documents what I'm doing. Negative row 1 plus row 2. My answer back in row 2. That kind of helps me out. So over here I write down the coefficients. If I multiply row 1 by -1, I have -1, 1, -3, and -4. And then my second row doesn't change yet, but I'm going to add these coefficients together, and I get 0, 3, -5, and 6. So I'm going to put that back in my matrix. It takes a full sheet of paper to do one of these problems. Just deal with it because that's what we're going to do. There's my first row. Here's my second row. And my third row hasn't changed yet. Alright, the next thing to get rid of is the 3. I have to use the first row to do that. So for the first row, I'm going to multiply it by -3. -3 times row 1. Add it to row 3, put my answer back in row 3. So this becomes -3, +3, -9, -12. And I'm going to add that to 3, -1, 5, and 14. So here's my new row 3, 0, 2, -4, and 2. From here, before I rewrite my matrix again, see how I have even values? All 3 of these are even. That means I'm going to take row 3, which is what that row is, and I'm going to multiply it by 1/2. I'm going to put that back in row 3. So that means the row that's going to go in there is 0, 1, -2, 1. Here's my new matrix. 1, -1, 3, and 4. 0, 3, -5, and 6. And 0, 1, -2, and 1. In order to put this in triangular form, I have one more thing I have to do. I have to get rid of this term. The only row I can use is the row right above it because of the zeros here. If I use the first row, I'm going to start introducing a number back in here, and that's what we don't want. So, to get rid of the 1, I'm going to multiply the third row by -3. To that, I'm going to add it to the second row, and I'm going to put my answer back in row 3. So the second row doesn't change. If I take the third row, it's 0, -3, 6, and -3. To that, I'm adding 0, 3, -5, 6. When I add them together, I get 0, 0, 1, 3. So here's my final matrix in triangular form. 1, -1, 3, and 4. 0, 3, -5, and 6. And 0, 0, 1, 3. From that, we can solve the system, because from here I know that z is equal to 3, because remember, when we go all the way up here, the third column is z. The third column is still z. Z is 3, and then we take that and substitute back in here. This equation becomes 3y minus 5 times z is equal to 6, and when you do that, you get 3y is 21, so y is 7. Finally, we take those two answers and we solve for x. X minus 7 plus 3 times 3 is equal to 4. You solve all that. X minus 7 plus 9 is equal to 4, and you get x is equal to 2. So my final answer is 2, 7, and 3. And we will work more of these problems in class to get you used to this notation.